Hello everyone, welcome back to day 40 of Coding Every Day. So today is a Monday, February 24th at 3:12 p.m. So I'm going through this roadmap here and I'm currently on that dynamic programming section, still kind of working through it, trying to learn the patterns and everything. So today we're going to look at maximum product subarray. So I haven't looked at this problem at all yet. It looks kind of like an array problem, so let's see. Given an integer array nums, find a subarray that has the largest product within the array and return it. Okay, find a subarray that has the largest product within the array and return it. Okay, a subarray is a contiguous next to each other in sequence, non-empty sequence of elements within an array. You can assume the output will fit into, all right. So I'm guessing it's like substring. Okay, so we have to find the largest product. Okay, because there's some negative numbers, but of course 2 negatives is a positive. So if you have like, you don't want to just avoid negative numbers, because if you have like -2, -4, you'd want to multiply them together, etc. Okay, so if we draw this as a decision tree, so our product, we can start with 1. Well, I guess we could start with the first number. Okay, well, the brute force way to do this would be, okay, so the brute force, so we'd start with empty list. The brute force way to do this would be to generate all subarrays and calculate their products. So for instance, to generate all subarrays, you either take, so this is I = 0. So you either take the number or you don't. So here we'd have 1, and here we'd have empty list. Now I = 1. We either take the number or we don't. So this would be 1, 2. And this would be just 1. And this would be 2. This would be still empty list. Okay, so this will give us all subarrays here. Okay, so if I were to generate this code, so I guess first what I'll try doing is implementing the brute force solution, and then see if we can add the dynamic programming elements afterwards. So I'll call it generate subarrays, and so we have nums. So we need, at every step, we need I. So we need current nums and I. So current nums will be like this array. Or could we just, let me try it with just I. So the base case is if I is greater than or equal to the length of nums, we should return, okay. Well, okay, so that'll be the base case. Otherwise, we will, I think we need another one. I'll just call it like current. And if you see me looking over here, I'm just making sure I'm not muted. Okay, so current will be like this array that we're keeping. I don't know if there's a better way to do it. Then we'll have like all subarrays. Okay. And then we'll say here, oh wait, maybe we don't. Well, we can say current.append nums of I, and then we can call it again, generate subarrays of current and I plus 1. And then current dot pop. All right, so here let me just try printing out first, and I can also return print 1 subarray equals, and then we'll just say current at this point. Okay, and we'll start it with what does current start as? So obviously I is going to be 0, and I guess current would just start as empty list. All right, so let's see, and then at the bottom I'll just return 0. Okay, so let's see what this prints here. I'm not calling it again afterwards, so you have to call it twice. One with the numbers and one without. There we go. Okay, so this is like the DFS type thing. So we see all of them, and then we pop this one. That's when this gets called, and then this. Okay, so we should expect that there's probably so the input size is 4, so I think it's 2 power 4, so 16. So this should be 16. 4, 5, 6. All right, instead of messing that up, I'll just have a variable called total. So this is just debugging. I just want to make sure that there's 16 of them. Total is not going up by 1. Okay, 16. Great. Okay, so we've generated all subarrays. And now how we'd want to do it. So for the brute force solution, we'll probably have something called like max product equals negative infinity. All right, and then here we'll just calculate the product. So this product, I guess I could just call it product equals so to get the product of an array, well, you'd say for I in range, or you'd just say for num in current num times equals so this is how you do it. So you set the product to 1, and then you just multiply it by every number in num. So how would you do this in list comprehension? Well, I'm not even making a list, really. Because list comprehension usually either maps a list, well, in this case, it's folding the list. I don't really know how to fold with list comprehension. Okay, so, all right, so product times equals num. And then we'll just say that max product equals the max of itself and products, like that. And then we'll return max product. So this would be the brute force solution here. Okay, so, okay. So I think my interpretation of the problem is incorrect, because here I have 8 because I chose 1, 2, and 4. but the correct answer is actually 4. That's because I'm doing just all like combinations, but there can't be any space in between. It looks like there can't be any space in between the numbers, so we can't go 1, 2, skip it, and then go 4. So let me retry on how I would do this. So let me rethink the decision tree. So we could start with empty list. So the first option at I equals 0, we can either add it or not. So let me just make it a little smaller. So here we would add it, and here we would not. So once you add it, once you stop adding something, it's basically that branch is dead. So you can't like not add something and then add something again. So whenever you go to the right, it's beat. Like you're just, this run is dead. But unless it's in this case. So if I have, just so I can conceptually understand this. So if we have, let's say the array is 1, 2, 3, 4, like this. Then we can have just 1. We can have 1, 2. We can have 1, 2, 3, 4. We can have 2. We can have 2, 3. So this kind of looks like n squared behavior. 2, 3, 4. Then we can have 3. We can have 3, 4. And that would be it. So this is like n squared, and what I mean by that is, so you would have I, and then like j would go to the end. And then I would just go up by 1 every time. So what's the time complexity? It doesn't tell me. Is it under? No. Okay, so it doesn't tell me the recommended time complexity. Well, if you do it this way, so maybe instead of generating everything there, we can have a double for loop. So let me just comment this out for now. We could have 2 pointers. So we could say for I in range length of nums, and then for j in range length of nums. Then we'd have like one subarray. I forgot 1, 2, 3 here. This is all of them. 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay, so here it's you're appending basically ij. So you're going until j is so you're starting at I equals 0 and you're going while j is less than 1, then less than 2, less than 3, less than 4. Then here I equals 1. Okay. So is it just while I is less than j plus 1? Well, we could say that it goes from 1 until length 0, 1. So the length here is 4, and we want it to go, yeah. So while I is less than j, subarray dot append j, right? Well, I guess we would want it like this, and then we would append j. So j equals 0. Well, we would append I, actually. Huh. So j is the inner loop, so that's this is going to be j. And then I guess... So do we need 3 pointers? And then would we have like k move up? So would you say every time you do this, you could set k equals 0, and while k is less than j, do this, k plus equals 1. Let's print here I, j, k. I just want to get this behavior first. Okay, so we have 0, 1, 0. Is that what I want? So here we add, so added subarray from I to k. Okay, so 0, 0. And I guess I could print what nums of I to k like this. So I want to add 1 first. All right, let me before I code, let me understand what's going on here. So I want to generate all of these. Is this not just like... Well, the simple way to do it, I guess, would be just subarrays dot append nums of I to j like this. Like that. It might be off by 1. Maybe j plus 1. Okay. So this looks right, but I'm getting a lot of empty lists, and I don't know why. So this behavior is correct. Then I'm getting empty lists. Oh, it's because... Okay, so here we want to say j equals I, and then we'll say while j is less than length of nums. Like this, right? It's because this will 2, 2, 3. I know I have a different test case, but it's pretty similar. Okay, so 1, so there's 4 here, 3 here, 2 here. Okay, this looks correct. All right, so this generates all the subarrays. The only problem is this part. So this is kind of like n squared because, or sorry, n cubed, because this is... I was just wondering if there was a better way to do this. I guess not really. All right, let's just do before we optimize. That's something I've been working on instead of optimizing, just getting the problem done first. So let's just continue with the brute force solution. So we'll say for subarray in, I guess I'll call it for sub in subarray. We want to calculate the product of that. So we'll say product equals 1. And here we'll say max product. Float Okay, product equals 1. So for num in sub, product times equals num. And then after we're done calculating that, we'll say max product equals max of max products. Okay, this will probably get TLE. Okay, so this is the brute force solution. Okay, this is the brute force solution. So now we can think. So now it's problem solving. So where are the repeated subproblems, and what information about those subproblems can tell us where we can save calculations, and where can we determine that we don't need to do something again? So could we keep, like, as we're generating subarrays, could we so the only trick here really is the negative numbers. We can't just discard anything with a negative number. So we do know something kind of. So like if the number of negative numbers is odd. So like if we have 1 negative or 3 negatives or 5 negatives, then the product will be negative. So I could trim it a little bit where if any of these that we encounter, any products are positive, we can discount any that have an odd number of negatives. All right, so if we look at 1, 2, -3, 4. We also have -2, -1. So in this case, as a human, so let me just think about how I solve this as a human. So I see that 1 doesn't do anything, so I kind of just ignore it. Doesn't really matter if we have a 1 in there or not. It's not going to change it. 2 is biggest, like the biggest thing we've seen so far. -3, I am looking ahead to see that there's no other negatives. And then, so we need to somehow know like the number of negatives, or because for instance, if this was a -4, when I encounter this, I know that I want to take it because I can undo the negative by looking at this. So getting the amount of negatives in each subarray would be O of n. -2, -1. So yeah, I'm a little stuck. Like I don't know exactly where to look on how to save time. So here, right, I see -2, but because I see that there's another negative up ahead, I know that we can take this negative. So something else I just thought of is adding a number to your, so like if this is it, we always want to take a number because it will always make our product larger no matter what the number is. So the value itself doesn't really matter at all. We always want to take it. The problem is the negatives. So maybe we just have to find the ideal starting location. Oh, maybe we could calculate like the product up until that point or something like that. So for instance, if this, we had it, let's say, all right, just ignore that big box. I guess I could delete it. So let's say at this point here, we had -5, like that, -5. So at this point, maybe we could do like a prefix product or something like that. So here our product is 1, here our product is 6, here our product is -30. Here our product is -30 times 8, so -240. I don't know what this is, so -240 times 9, and then -240, we'll just say times 9. So we could do this from every position, I guess. Well, this is basically, this is the brute force solution. But I was thinking, so the values do kind of matter because here, so we know that 8 times 9 times 10 is 720. And here, so if there's one negative, we can't take that negative. Okay, so here there's maybe this will extrapolate to multiple negatives, but so right now we cannot take this negative because there's only one negative. So it sort of like divides it into two problems here. So then we take the max between 720 and 6, which is 720. Okay, if we have two negatives, then we take the whole thing. I think determining the count of negatives is really important because we only, so we should always take the full, if we ever have an odd amount, so if we ever have an even number of negatives, we should always just take every single number no matter what, because that will result in the biggest product. So if we had like 6, 5, 8, 9, 10, and let's say 2, right? And let's say we have -6 and -9. It doesn't really matter anything at all. We can just sum all, or we can take the product of all of these, and that'll give us the biggest answer. So we kind of want to find the longest, not necessarily the longest, but the subarray with the biggest value that has an even number of negatives. So maybe what we can do is look at this. So this is valid because it has 0 negatives. This is valid because it has 0 negatives. This is invalid because it has 1 negative. You know, same with this and this. Now this is valid again. Okay, so I think let's reduce our problem size by half and say that, so if, I'll just write this down. So if nums contains even number of negatives, then take products of all numbers, because they have to be integers, right? Like they can't be like 0 point. Yeah, integer array. Okay. Because if it was like 0.5, it would be a little trickier. Okay, so yeah, if it contains an even number of negatives, then we should just take the product of all numbers. So let's only, so that's true. So let's only look at examples that have an odd number of negatives. So let's say we have 3 negatives in some example. I'll use this yellow here. Okay, so let's say we have 1, 2, 4, 6, 5. I'm just doing random numbers basically. And 3. All right, and let's say we have this is negative, and this is negative. Okay. So we can kind of just eliminate any subarray that has a odd number of negatives. So if we look at this one, maybe we could store the positions of the negatives. Okay, so if I index all of these, so we have 0, 1, 2, 3, 4, 5, 6, 7. So we know that our negatives are at position, let's do it like that, are at positions 2, 4, and 7. So that means our candidates are either from 2 plus 1 up until the end. So from 3. So from 3 till end is one candidate, this one. And we can deduce this just from the numbers here. So 3 to the end, we know that start until 6 is another candidate. And we know, is there anything else? I guess another candidate would be 5. No. So we need to include 2 of these. So we either have basically like that. So you either have like everything on this, like everything up until 7, or everything after 2. So this kind of helps us narrow down the problem, because we can assume that adding more numbers is always good as long as you have an even number of negatives. And then we can just take the max of these. So we either have this here, or we have this here. Okay, so what about if we have 5 negatives? So instead of writing out the numbers themselves, I'm just going to write out the positions of the negatives. So if we can simplify our problem to the positions of the negatives maybe. So let's say we have negative, and let's say we have a negatives at position 0, 2, 5, 6, and 9. So now our problem is on this. So what are all of the subarrays here that we consider? So it has to include an even number of negatives. So we can include everything up until 8, everything up until 4. But if we're going to do that, okay, so now this is interesting. So we could include everything up until 4. But if that's the case, we know that everything up until 4 will always be smaller than everything up until 8. So we don't have to calculate that at all, because we are assuming that adding more numbers always increases our product as long as there's an even number of negatives. So, okay. Or we can do everything after 0. So I think this problem, I don't know if I'm missing something, but so far I'm understanding if there's an even number of negatives in the whole problem, okay, well, it does get a little bit more interesting than this. Let me just finish my previous thought. So you can just compare those two, right? So like 1, and I'll just say E for n. So you like 1 to E and S to 8. So 8 we're getting as like the last negative index minus 1, and and 1 we're getting as first plus 1. So 0 plus 1. But this problem does get a little bit more interesting. So for instance, what if the negative value here is really big? Well, I guess it doesn't really matter because it's included in this one anyway. We can't include, like I was thinking, what if this is a really big number and this is a really big number and we want both of them? Well, it's actually impossible for us to include both of them because that would mean we have an odd number of negatives. Okay, so let me just try coding this and see if I run into any problems. And let's also look at the examples here. Okay, so here we have in the first example, so let me delete this. So in the first example, we have 1, 2, still not muted, -3, and 4. So our negative positions, so first of all, we check, do we have an even number of negatives? That's kind of like a base, I don't really know what you call that. It's, you just return the product of the whole thing. So no, we have an odd number. So it's at position 2. So let me just index these real quick up here. 0, 1, 2, 3. Okay. So we have it at position 2. So that means we can take the max. So now we generate 2 products. So from 0 to 1 and from 3 to end. And we can also define that as s to 1. So here in this case, we take the max of those two and we see that 3 to the end is 4 and this is 2. So 4 is greater than 2, so we return 2. Or sorry, 4 is greater than 2, so we return 4. And this one is even number of negatives. Okay, so let's try coding this here. So I'll say, so let's first get the number of negatives. Okay, so num negatives is equal to 1 for x in nums if x mod 2. Okay, so if x mod 2, no, we don't want x mod 2. We want if x less than 0. And it might be greater than or equal to. So if it's a negative, okay, so if x is negative, we'll add a 1. So we can just take this, so the length of this is equal to nums of negative. So this will get me all of the negative numbers, and then also, can it be 0? Yeah, so num could also be 0. Okay, so that's something I did not consider either. So we want to avoid zeros, so that's something we're also going to have to think about. So the length of this array is the number of negatives. So if the number of negatives mod 2 equals 0, then we can return product of nums. And let me just make a function called product. I don't think this exists in I don't know if you can do it in list comprehension. Could I say like x times, maybe I could say I could say I could say nums of I times nums of I plus 1 for I in range length of nums minus 1. Maybe this could be it. But it's like a weird edge case. I'm just going to make it, so this will take an array or a list. I don't know what you would call this operand. I'll just say like numbers or like a list, number list. Okay. So we'll say P for product equals 1. So first of all, if not number list, so if it's empty, we will return 0. It has no product. Otherwise, we will say for num in number list, P times equals num, then return num. Okay, so that will be our product. There. Okay, so this is kind of like the base case. All right, so now, and the zeros might throw off the whole thing. I'm just going to code this and then see if the zeros, so okay, so this is good. So if we have an even number of negatives, then just return the whole thing. Otherwise, maybe when we do this, we could also store the positions. Yeah, let's say negative positions equals empty list, still unmuted. All right, and then we'll say for okay, sorry, I had to sneeze. So for num in nums, let's say actually for I in range length of nums, then we'll say if nums of I is less than 0, then negative positions dot append I. So if we have a negative number, we'll add it here. So then we can just take if the length of that. Okay. Otherwise, let's say that so the left half product equals the product of nums. Okay, so let's get first negative equals negative positions of 0. And we want to calculate everything from first negative plus 1. So let's get nums of first negative plus 1 like that. And then, well, I guess this would be the right half product. So excluding first, and this will be excluding last equals product of nums of, we'll just say last negative so up until the last negative like that, and then we'll just return the max of those two. All right, and let's see if we get an error here. So this one I output -1. Okay, so here the length should be, so let me print negative position. So I'm thinking the length should be 2. So here negative positions is 2, here it's 0, 1. Okay, so my product function, I suppose, is not working then. So P equals 1. Let me print. Okay, so that's so product is not working. Number list. All right. Instead, let me just so this function isn't working. So let's just isolate this problem. So product of number list. Let's just print it and return 0. Sorry, nums. Okay, so here output is 0. So why is it not 1 times 2 times... Okay, not really sure why this is not working, so let's just pick it apart here. So num equals 1. And let's print p equals... Oh, I'm returning num. My bad. All right, so this that should work. So I was returning num instead of p. So it was just for the product, it was just returning the last number instead of the product. Okay, so all right, I think that's a valid edge case. So if length of nums, so if it equals 0, can it equal 0? No. Okay, so if it equals 1, then I'm just going to return that number. So let's see. I think I'll fail with zeros here. Yeah, 0. Okay, so we passed 10 test cases though, but the zeros are tricky. So we have to just avoid zeros. So if, well, not necessarily, because okay. So zeros are greater than 0 is greater than negative actually. So okay. Let's do another example here. So if we have 1, 2, -3, 2, 0, 5, 6. Actually, let's say 1, 3. Okay. And 0. So 0, you can think of it like splitting it, right? So we split it by zeros almost. Because we know that if there's two numbers, we will always be able, okay. So if length of nums, I'm going to make this statement, is greater than or equal to 2, then the answer will always be positive. Okay, so there's a couple different scenarios with length equals 2. So we have negative, 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 positive, positive, negative, and positive, positive. So in this case, the product is positive. Here we just pick the positive. Here we, same thing, pick the positive, and here the product is positive. So we never have to worry about the length being less than 0. So we can consider that the floor will always be 0 as long as we have at least two numbers. So we kind of want to just avoid 0. So it's almost like we want to do exactly what we're doing with everything, but we want to split it by zeros. So I almost wonder if I can just do that. So it's almost like we have different subproblems now. So we take this subproblem. So maybe we split it by zeros and then solve each subproblem. So maybe I could say subproblems equals nums.split. Well, split takes a string. I mean, so we could convert it to, I mean, we could do this. Let me just see if this works. I'm kind of curious. So if we join them and then we split them, num string dot split, and we split it at 0. And I print subproblems. Return. Okay, let's see what this looks like. Expected string integers. Sorry, expected string instances integers found. So nums. Nums is a list of integers. We're supposed to do, okay. So let's map. Let's map everything to a string. Is there a way to split it by several? Delimiters? Like that? Does that work? Or we could just do a manual function maybe. Okay, so either way, would this work? I guess so. So I think I'll just do a manual split at the beginning. So okay. So my plan is split by zeros and then solve each subproblem. So to solve each subproblem is okay, so then solve subproblem. So to solve okay, so this is O of n. Solving a subproblem will be several steps. So I'm just going to do this last thing before I code it. So to solve a subproblem, we must get number of negatives, which is O of n. Then we must take the max of two numbers. Well, first we have to calculate product. So we'll say calc, I'll call them head and tail products. So that's like excluding the first negative and excluding the last negative. So that's also O of n. These are not nested though, they're separate. And then we basically just take the max product of those, which is constant. So this whole solution would be n squared. But is it though? Because if n is the original size of our list, we're basically doing n here. Well, we're doing this. Okay, let's say that k is the length of our subproblem. Then it's k at most n times. But k, I wonder if it just is n though. Because we know that the sum of all k equals n. So I actually think it's not that bad. All right, so let's write the split by zero function. So let's just say parts will be empty list, and we'll say part is empty list. So while num does not equal 0, parts dot append, then we'll say while I is less than length of nums equals 0, still not muted. Okay, so while num does not equal 0, we will append nums of I. And this will be nums of I. So while it doesn't equal 0, we'll add it. And we'll keep going until it doesn't equal 0. When it does equal 0, we'll say parts dot append a copy of parts, and then part equals blank. All right, so let's print parts. Is less than length of nums. How's that out of range? I should never be equal to Is it telling me that there's no 0? Nums of 0? Is nums of... How is nums of 1 out of range? Wait, it's telling me that nums of 0 is out of range. List index out of range. So it prints it. Am I missing something? Oh, is it because of right here? Oh, I see. So while length of nums, while I is less than length of nums. Like this maybe. Because if there's only one part. Alright, and then what's the problem? Alright, so this looks good. What if I say nums equals, and then let's do this example. So if we have 1, 2, negative 3, 2, 0, 5, 1, 3, 0. So it should give me 5, 1, 3, and then those. Okay, perfect. All right, so this will get us all the parts. Okay, perfect. So now we're basically going to say for subproblem in parts, solve this. So we'll say here max product equals negative infinity, right? And then, okay, so each loop well, I guess we could have a function called get products of subproblem, product of sub, which takes in a subproblem and returns the products. And it'll be this. So this will return the subproblem. And then what we want to say is, still not muted. All right. So we'll say P equals, what is it? Product of sub. I guess we'll just say max product equals the max of itself. And product of subproblem. Return max product. Alright, does this give me an error anywhere? Yep. Okay, what's wrong with this one? 0, 2. I return 0, but it should be 2. So it should get caught here. So let me print out subproblems. Or parts. So print parts. See if we have the right part or if we don't. So here part is correctly identified there. Part is empty list and 2. Okay, so part here is an empty list. Print subproblem. Okay, results. Let's just get it here so I can debug it. Like that. Result 0. Oh, is it because I'm returning nums? Okay, so instead of nums of 0, I want subproblem of 0. Subproblem. Why do I have product here? That's weird. So instead of nums, okay. All right. Oh, that's not what I meant. All right. Sweet. All right. Okay, we got there. Okay, so split problem by zeros. This function is kind of awkward in there. What happens if I do it here? It will still work, right? Yeah, okay. So that's better there. So solve each subproblem. Split problem by zeros into, let's say, subproblems. Okay, helper. Okay, and then here we solve each subproblem. And then we'll probably clean this up a bit. So negative positions I'll call neg pos, or maybe just negatives. And then here, instead of first negative, we can say negatives of 0 plus 1, negative of 0 minus 1. That. Okay, can I make this less lines? Yes, definitely. So we're basically just filtering out. So it's the negatives equals I for I in range subproblem if subproblem of I is less than 0. So this should work. Wrong answer. Length. Okay. Okay. Cool. This feels like dynamic programming. Just I don't know if it is, but it feels like I'm using the nature of the problem to save calculations. Like for instance, I'm using the assumption that more numbers is always good, unless it's an odd number of negatives. So I feel like that part of it is the dynamic programming, that I basically only have to do these two calculations and take the max of them. Yeah. No, that looks bad. Okay. Great. So that's that. Cool. Wow, I really had no idea for a minute there what to do, and I was able to kind of just think about it with the negatives and the zeros. I think that, like I said, the key realization for me was you always want to add more numbers, always, if you have an even number of negatives. So yeah, thanks for watching. This was a fun one. I enjoyed this one a lot, and glad I was able to get through it in about an hour. It took, still need to get better at these for like interviews and stuff. Taking a little bit too long to do them and all that, but it was still good. So thank you guys very much for watching. Today was day 40, and I'll see everybody tomorrow for day 41.